Hello, and welcome to Shimadzu's Theory and Key Principles series on gas chromatography. This is session 8, where we'll be looking at maintenance and troubleshooting for GC. My name is Andrew Clissold. I'm the GC manager at Shimadzu, and I'll be your presenter for this session. This is the 8th session in our Theory and Key Principles series on gas chromatography. If you missed any of the previous sessions, I recommend you watch these first, and then sign up to the next available slot for this session. All previous sessions are available on demand and can be accessed from our website. This session focuses on basic maintenance, looking at the key areas where regular maintenance is advised. Loosely, this can be broken down into inlet, column, and detector maintenance. Let's start with the most important one, inlet maintenance. As we discussed back when we looked at the splitless inlet, if you mess up the inlet parameters, it all goes wrong. The exact same thing is true when it comes to maintenance. If you have an issue, the GC inlet is the most likely candidate. Frequent maintenance is therefore extremely important. So let's look at what needs looking after and when. The septum will likely be the most commonly replaced part on a GC system. Any GC with a liquid injector, such as an SPL, PTV, OCI or MMI, will need a septum replacement. This is typically done around every 100 injections. Each time the septum is pierced by the needle, it creates a small hole in the septum. As these holes multiply through repeated injections, bits of septum can break off. This is known as coring. Not only do these broken pieces increase the chance of air leaking into the inlet and carrying gas out, they can also become active sites within the liner, resulting in peak tailing and lower analyte response. The septum can also become a source of contamination, either through the release of siloxanes as the septum ages, or through sample contamination due to prolonged usage. There are a range of septum types available. Firstly, you must select one which is designed for your GC's inlet. Septum shapes and sizes vary significantly from vendor to vendor. Most vendors also offer a range of septa with various properties, such as low bleed, long lifetime, or high temperature. The liner can also suffer from contamination, as one of its main purposes is to filter any non-volatile material from the sample. This helps protect the column and detector, and is important even when running assumedly clean samples and standards. The frequency of liner replacement varies, and is based on the application and sample, but typically is replaced every 20 to 100 injections. The liner O-ring should also be replaced at the same time. This can become brittle over time, causing leaks. Like with the inlet septum, liners come in a wide range of sizes and shapes. They are also very specific to instrument vendor, model, and inlet type, so be sure to select the correct one for your instrument. They tend to be categorized by injection mode, either split or splitless. In split mode, we have a high total flow through the liner, so the design is open to prevent any bottlenecks. With splitless, we have a much lower flow, and need the full sample to transfer onto the head of the column. These liners have a taper at the bottom, to direct the sample towards the head of the column. There are also liners that try to offer the best of both worlds. These are suitable for low splits, say around 20 to 1, and for splitless work as they have a very small taper at the end. They aren't as effective as a dedicated split or splitless liner, but are often suitable for a wide range of applications. The next consideration is whether or not we have glass wool. Glass wool is used to help to improve the vaporization of analytes by increasing the available surface area. It does, however, offer a high degree of reactivity, so can cause issues for some applications, for example pesticides. The final decision is whether to have any form of deactivation treatment. Vendors will offer the option to have a liner treated in some way. There are a range of deactivations available, and these depend on the supplier, as they all have their own different techniques. All these options can seem a bit overwhelming, but for maintenance, the most important thing is that you replace like for like. Swapping to a different type of liner will almost always affect the chromatography in some way. The final part of inlet maintenance, which is often overlooked, is the split filter. This filter sits in the flow path between the inlet and the flow controller, and prevents any contamination damaging the highly precise flow controller parts. This filter typically requires replacement every 12 months, and is usually exchanged during the preventative maintenance visit by your service provider. In applications where neat sample is injected, however, the contamination can build up faster, requiring a more frequent replacement. Modern GC systems have indicators to highlight when the filter is saturated and when it requires replacement, and many now are exchanged without the need for tools. So that covers what's required for inlet maintenance. All of these parts should be replaced while the GC system is cool. All heated zones, such as the inlet, oven and detector, should be cooled to below 50 degrees. After this, the flow can be turned off and the parts exchanged. The flow should then be turned on for a few minutes to purge any air from the system before the heated zones are turned on again. In total, the instrument is usually out of action for 1 hour, and most of this time is simply waiting for the system to cool down or heat up. The actual time to perform the maintenance is around 10 minutes, or less for an experienced analyst. Moving on, we can now look at the second area of maintenance, the GC column. It's fair to say, column installation requires a fair amount of skill. Whereas the liner and septum exchange can be learnt after one demonstration, column installation may take several attempts to perfect. There are 3 stages involved: trimming the column, connecting it correctly to the inlet and detector, and correctly conditioning the column before use. To trim the column, we typically use a ceramic wafer, a small white rectangular piece of ceramic which usually has the GC vendor logo on it. These wafers have 2 types of edge on them: a smooth edge for cutting fused silica columns, and a serrated one for cutting metal columns. It's important you use the correct edge for the correct column. Try gently brushing the edge over your finger to feel the difference. Once you've got the right edge, you need to ensure we perform a clean, perpendicular cut on the column, about 5 to 10 centimeters from each end. There are different techniques for doing this, and it's difficult to explain in a picture. We'd strongly recommend you watch one of the many videos available online from the major column suppliers. Your cut column should be perpendicular to the length of the column and should have no rough or fractured edges. It can take practice, so test your skills on an old column first. Using a magnifying glass to check your work can also be helpful. Ideally, you should only cut the column after the nut and ferrule have already been put over the end. This prevents any debris, like graphite from the ferrule, getting inside the column. We'll talk more about the different types of ferrule in more detail soon. To install the column, you must follow your GC manufacturer's instructions for the specific model of GC and specific inlet and detectors you're using. There will be specific measurements on how long the column needs to be above the ferrule. It is vital you have this information, as it determines where the tips of the column will sit inside the inlet and detector. Fortunately, many GCs now come with a specialised tool, allowing you to measure the correct length easily. If this isn't followed, it can produce poor peak shape and sensitivity, and could even prevent your flame-based detector from igniting. Once your column is installed, you need to ensure all the air is removed from it by flushing it with carrier gas for around 5 to 10 minutes at ambient temperature. Once the column is purged, the column can now be conditioned. Again, you should follow your column manufacturer's own instructions for this, but conditioning typically involves slowly heating the column to 20 degrees above the final analysis temperature for around 1 hour. The exception here is if your method already reaches the maximum allowed temperature. Never exceed the maximum temperature for the column as indicated on the column packaging. As mentioned earlier, we need to discuss the various ferrule options available. Ferrules are used to seal the column to the inlet and detector. There are 3 main materials used for them, each with their own advantages and disadvantages. For GC analysis, most systems use graphite ferrules as they're the easiest to use. Graphite is very soft, so the ferrule molds easily to form a tight connection, and over-tightening slightly poses minimal risks. The great thing with these is that they stay in place once they've been tightened onto the column. They can be removed, but won't slide up and down the column of their own accord. The downside with graphite ferrules is that they're air permeable, so can't be used in vacuum systems, like MS or SCD. To overcome the air permeability, graphite can be mixed with a harder material called Vespel to form a hybrid graphitized Vespel ferrule. These are the most commonly used ferrules for GCMS. By adding a harder material, over-tightening does become slightly more problematic, so some care does need to be taken. The main downside of Vespel ferrules is that they can move around even after they've been tightened, which can make installation a little more tricky. They also have to be retightened after a few heat cycles as the material tends to shrink. The final option is the metal ferrule. These make a permanent connection with the column, so cannot be removed without cutting. This can be helpful, as it overcomes the Vespel issue where they can slide around during installation. They also arguably offer the best seal, making them particularly attractive to GCMS users. The main downside of metal ferrules is that over-tightening them, even slightly, can break the column. This can happen immediately or after several heat cycles, meaning you are more likely to have overnight errors due to column breakages. Metal ferrules are far less forgiving than the other 2 variants. While superior, they are perhaps not recommended for apprentice analysts. Periodically, it is necessary to trim the front end of the column to remove contamination. Even if you use a liner with wool, some non-volatile component can still make their way onto the column. This can impact peak shape, peak area and retention time. Usually the front end of the column is trimmed by about 15 to 30 centimeters, depending on the length of the column. This helps remove the most contaminated part of the column to give it a new lease of life. On a 30-meter column, it's possible to lose several meters before resolution is significantly impaired. But do remember, adjust your retention times, as all these will shift slightly after trimming. To avoid this, some analysts prefer to use a guard column before the analytical column. This is exactly the same as the retention gap we used on the OCI, but usually has the same inner diameter as the analytical column. A few meters of fused silica, without any phase, means this section can be trimmed with no change in retention time. It's actually possible to purchase some columns with guard columns built in, removing the need for the additional column connections to join the analytical and guard columns together. These are popular in applications where samples are very dirty, such as clinical labs where urine and whole blood are analysed. The last area of maintenance to consider is the detector. Fortunately in GC most detectors require very little, if any, maintenance, often lasting several years without attention. There are, however, quite a broad range of detectors available, and each one works rather differently. There isn't time to cover all of them, so instead we'll focus on the most common one, the flame ionization detector. We'll cover MS maintenance later on in this series, when looking at GCMS in more detail. The FID is the most popular detector, and fortunately it has very minimal requirements. There are three main parts of the FID that may require some attention. It might be necessary to trim the back end of the column from time to time, as this can get damaged by heat if the detector temperature is high. It might also be necessary to replace or clean the jet from time to time, as this can get blocked with contamination, preventing it from lighting. Finally, the igniter itself might get worn, a bit like the igniter on a gas hob, so it can be necessary to replace this as the instrument ages. Unlike other maintenance, these tasks are typically done once a fault occurs, or during an annual visit from a contracted service engineer. That concludes our overview of maintenance, and so now we will move on to the second part of this presentation, looking at general troubleshooting in GC. When it comes to troubleshooting, it's always better to not have to do it. Preventative maintenance, like the steps we've been discussing, will significantly reduce the need for troubleshooting. And many of the steps we've spoken about should act as a first point of consideration if a problem arises. Troubleshooting is something that you can spend an entire lifetime learning, and no amount of time would allow us to fully train you on how to do it, but hopefully this short introduction should act as a good start. Believe it or not, the overwhelming number of technical issues in chromatography are, yes you guessed it, human error. When dealing with an issue, always remember the golden rule. Check the obvious stuff first. For example, is the GC powered on? Is the GC in the computer connected? Are the gases plumbed in and are the cylinders full? Is it the correct gas at the right pressure? Have I checked my batch for typos? And are the vials in the right place? Now this may sound silly, but double checking these things will save you a headache and make for a fast resolution. Assuming all that's checked out okay, you can now start to look at identifying the cause of your issue. Firstly, check if the problem is repeatable. Is it really a fault or a fluke event? Consider if there have been any recent changes around when the fault appeared. Was maintenance performed? Has the nature of the samples changed? Diagnosing problems in GC usually involves running one or more tests. When you do this, make sure you only change one variable at a time. It may take longer, but you'll have far more confidence in your eventual conclusion. Lastly, as you'll see in the following slides, routine maintenance solves a multitude of problems, so this is always a good first step. In the next few slides, I will discuss some common issues found in GC and some suggestions on how to resolve them. This is not an exhaustive list, but covers some of the more frequent questions. Peaks that are not adequately separated is the single most common issue when operating a GC. In order to accurately identify and quantitate a peak, it must have baseline separation. This issue is not a mechanical one, and the GC is likely working perfectly well. Peak resolution is a product of the column and the applied method. To achieve suitable resolution, the analyst could try running the method for longer at a lower temperature, giving the peaks more time to separate out. The choice of column should also be questioned. In previous episodes of this series, we have discussed the different column phases and dimensions, and how these should best be matched to the analyte requiring separation. Finally, the injection volume should be inspected. Larger injection volumes increase sensitivity, but also produce broader peaks. A reduction in volume, or increased split ratio, can sometimes provide improved peak separation. A second common issue is poor peak shape, sometimes referred to as fronting or tailing. Pay careful attention to the images on this slide, as the two effects are distinctly different and have different root causes. Fronting, where the left side of the peak is too wide, occurs when the amount of sample on the column is too great. The stationary phase of the column is overloaded with the sample, distorting the peak shape. The solution is to reduce the sample volume, either with a smaller injection or larger split. If neither of these are appropriate, a different column is required, with a larger film thickness to accommodate the sample. Tailing, by contrast, is a difficult symptom to diagnose, as there are multiple events that can cause this. Typically, somewhere in the peak's journey through the GC, it has encountered an area that has caused a portion of the sample to be slowed down and tails behind. A system that is dirty or contaminated can cause this, as could any active sites in the inlet from worn-out parts. A small leak in the system or a poorly installed column would have similar effects. As a general rule, if you see one or more tailing peaks in the chromatogram, consider performing the routine maintenance discussed earlier in this session. Next, we have ghost peaks. This is a term used to refer to any peak within a chromatogram that the analyst believes should not be there and is not in the sample. A ghost peak represents some analyte that is being introduced to the sample during the analysis. The first step is always to run the GC multiple times, to confirm that the ghost peak is a consistent event and not a fluke occurrence. Second, the GC should be run without injecting a sample. If the root cause is somewhere in the GC, the peak will still appear. Ghosts fall into two distinct categories, ones with very consistent retention times, and those with retention times that vary. Each one is handled differently. If the retention times vary, then the ghost peak is hiding in the column. The peak is likely to be carryover from a previous injection that had not had time to elute from the column before the next sample was injected. In this scenario, lengthening the method to allow full elution of the sample will fix the problem. If, however, the ghost peak has consistent retention times, then we can conclude its origins are upstream of the column. This means either the sample inlet or the autosampler. Performing a manual injection with a fresh syringe will determine which one of these is the root cause. For the autosampler, a new syringe with fresh wash pots will remove any contamination. For the inlet, maintenance on the septum and liner will also remove the source of the ghostly peak. Another class of common concerns with GC is the quality of the baseline. These fall into a number of different subcategories. High bleed is an effect that sees the baseline rise up towards the end of a sample run. All columns bleed to a certain degree, so this is not necessarily a problem. If the bleed is excessive, however, this can affect the accuracy of the results. High bleed is always a result of the column. New columns that have not been conditioned properly, or old ones that are wearing out, have higher bleed. It is also possible to overheat a column, causing bleeding. Typically in these cases, the column should be replaced. Different from bleed is baseline drift. This can go up or down and indicates that something within the system is not being consistent. This can be the result of poor carrier gas quality or supplied flow not being consistent. Noise on the baseline can be the result either of electrical or gas flow issues, as well as contamination within the system. The same is true of baseline spikes. If these occur consistently, it would be wise to speak to a service engineer about how to proceed. Lastly, we should look at a few common issues regarding peak consistency. Variations in peak area can be troublesome and caused by a multitude of factors. Firstly, take careful note of any pattern in the area from run to run. Does the area consistently increase, decrease, or does it appear to be random? Increasing areas suggest a buildup of sample in the system, likely in the inlet. Decreasing area could indicate a progressive loss of sensitivity, either from sample degradation or deterioration of the detector. Random variations in peak area can be an issue with the method or potentially the autosampler. Check if the syringe is clean and functioning well. Shifting retention times indicate that the movement of sample into the column is at fault. This could be due to only partial vaporization of the sample, either because the inlet is too cool or the sample is overloading the liner. Also make sure the system is leak-free, especially the inlet. Peak width can sometimes be a problem if it is too broad. Wider peaks give less consistent integration and so poorer results. Broad peaks can occur either because a peak has spent too long diffusing in the column or because it was not focused correctly in the inlet. If the method is slow, consider raising the temperature and column flow to sharpen the peak. If using a splitlet injection, ensure the solvent focusing step has been performed correctly. That concludes our look at maintenance and troubleshooting. As you can tell, it's a very broad topic, and it's impossible to cover all aspects in a single session. Hopefully, however, this will give you a beginner's insight in how to look after your GC. Let's recap over some of the key points. Maintenance prevents troubleshooting, and preventative steps are always the best. Most issues arise from the GC inlet. Make sure to replace the septum, liner and O-ring frequently. The split filter should be changed periodically, and column trimming is always a good idea. Correct column installation is crucial. Use the correct ferrules. Cut the column properly, ensure the installation depth is accurate, and condition the column. Detector maintenance is infrequent for most systems, unless you're operating a mass spec. Troubleshooting. Always check the obvious first. Think about what might have changed. Change one thing at a time, and try and isolate where the problem is originating from. The next session will be on method development, bringing together the knowledge you have acquired so far in a procedure for creating working GC methods. I hope you can join us. If you'd like to receive the latest news from Shimadzu, including information on webinars, workshops and events, please join our newsletter by going to our website. If you'd like to get in contact with us, the contact details for UK attendees are on the screen now. For those of us joining outside the UK, you can find contact details for your local Shimadzu office by visiting the Shimadzu Global website.
Excellence in science. Shimadzu.